Welcome back to High Performance Computing, Advanced Scientific Computing, Lecture 5, Parallel Programming with OpenMP, Part 2. In Part 1, we had an interesting overview about OpenMP. So really looking at OpenMP perhaps from a 10,000 feet perspective, no large source code examples, but we understood the difference between serial and parallel regions. And of course, the idea of this portability that you have when you follow the OpenMP standard. So OpenMP is used for shared memory programming, hence the first part also here and there made some distinction between shared memory and distributed memory. And you already know from the previous lectures, distributed memory is largely done with the MPI standard, and we used an OpenMPI implementation. Right, so OpenMPI is not to be basically thought about the same as OpenMP. So OpenMP is really a standard for shared memory programming. We will talk about it also now in the second part in much more details, where you also think about then how we do this in HPC, how it became a parallel program of using OpenMP and elements like this. So this will be not a complete introduction to OpenMP that I also said in the first part, right? So there are definitively lots of approaches how you can use OpenMP for parallelization, and what we also learned later a little bit around data flow and task flow. That's how we end the last part when we think about new developments with OMS and so on, where we have a much more task and perhaps data pipeline view thought of things. Now let's dive into the material of the second part, and this will be largely around how we really program this and give you also some examples here and there, how this is of course then used. So the first thing is again, start thinking parallel. It's important to think about that we are not in a more or less normal software engineering program that we do. Many of you have this Java and then program some specific program in Eclipse or any other, let's say, environment. Here, we already have to think about, again, totally in parallel, and this for different reasons, because our code that we will have is, again, something which will be very instrumental to understand where are sequential regions in this code and where are parallel regions in the code, which I can, so to speak, use directives for that OpenMP provides to do parallelization. And there are many of those. One good example that I will give here also today will be loops, where these are typically good candidates really for parallel regions, where a team of threads can really work on the separate elements of the loops or windows of the loops or part of the loops, however you will call it, when you iterate through it. Others are additions, for instance, which also make sense. We also learned in the first part, just to revisit this a little bit, that we have this sort of master thread, right? This is shown here. You have a process that basically then initiates the master thread, but then this master thread is responsible with this OpenMP directives to really spawn new threads for helping. Then you end up with a team of threads, whereby usually the master thread here becomes also part of these team of threads. So will also survive, as we heard, because once I will spawn it and then in a way fork these different threads, the master thread will survive when we later also then join them again, or essentially stop the parallel region. So OpenMP in the end then gives you a certain piece of instructions and compiler directives, which are then really the basic building blocks we will look into today. Again, we cannot look on the complete OpenMP standard these days. This would cover at least 1 week to have a, from morning till end of the day lecture. So here we really picked the several pieces to really show you how it works with parallel computing, and here and there also how you can combine it with MPI. How that would look like when we again have our beautiful Hello World example. You see that a little bit, and we also were looking in the first part already to one application, which was the the highly parallel DB-scan implementation, where we thought, okay, this is not only an MPI program, It's a hybrid program. That means we did MPI combined with OpenMP. You don't have to do it. In earlier lectures, I showed you also there's a run just with MPI, but we have seen to approach more linear performance and speed up, right? Then it makes sense to think about to really leverage the shared memory in the node, and then of course across the nodes have the bigger program. And hence we have seen in that job script that we shown there that we have a certain command in the job script called export OMP number of threads that you see essentially here. So that's a very important parameter where you then define in the job script that we will have 4 threads available. So why is that important? Because in a way you can see again, similar with MPI when we steered the number of tasks essentially outside in the job script, right? Not inside the program. This enables scalability, not knowing a priori, so to speak, how many real threads you need at the compile time. So this is something where you see that here a little bit with our beautiful Hello World program. We have here this Sentinel Pragma OMP parallel. In other words, what's followed should be executed in parallel. We don't even need here, let's say, some brackets or so. We just want to have Hello World in parallel. But you also see in the source code very beautifully, I don't tell anything about the number of threads, right? So this is inherent scalable. So no matter what I have in the job script that I can give to the scheduler, this will be responsible basically when we execute this on a HPC machine, that this will be now spawning, as the name suggests here, this Pragma OMP parallel regions, the number of threads we indicate in the job script. So this will be executed 4 times. The same code, right? In the end, we just parallelize this here 4 times, this one statement, and come out to this execution when you want to do this. With another view, you see here, we have this master thread starting the main program, and then the master thread becomes the T0, the thread 0, as I was alluding to. It remains as part of the team of threads, but is also, let's say, really forking 3 other partners, right? Partner threads that work then on the parallel region, because we indicated this was number 4, and then it will be executed 4 times. So I think this is really easy to follow, but also important is now to understand that here we don't really explicitly program in parallel in send and receive as you have done with MPI. You don't really need to allocate buffers as we have in MPI. We, send receive messages, for instance, and reserving buffer space for having your messages in that you want to send or actually to receive. You see that this compiler directive is a sort of meta programming, so it's not part really of the real program flow, but you instrument the code with these and then enable parallelization. So it's another way really how you do parallel programming. Looking on a bit more sophisticated program, and as I said, I will do here in the course just the very simple things in OpenMP. You can come to quite some interesting OpenMP programs, which are very elaborate and really get the good performance out of your memory. So think about a more sophisticated Hello World example for the reason here that we also want to get some information out of the OpenMP environment. And again, there's a kind of small similarity to MPI, because we want to have certain numbers known, right? When I put and steer this in the job script, the number of threads, maybe it's useful for me as developer to still work with this in the program. So there must be a way that the OpenMP environment is giving that to us, similar like the number of ranks, right? I would have in an MPI program. And you see that a little bit where we prepare this here. I mean, firstly, we have to have the headers of OpenMP, the library in, similar like we also did with MPI, of course. But then you reserve here the integers, number of threads, and the thread ID, with the idea that we actually get some information now out with this OMP get thread num. And this one is a bit special, because if you think about that, now everybody is executing this from all of these number of threads, let's say 4 that we said initially, then I need some variables which are not shared. You remember the shared address space, right? So when I have now a normal variable and I want to have a unique ID, what thread number I am, right, in the number of world of threads. There's nothing like really the communicator com world that you know from MPI, but there's an idea that I will determine, or I'm able to determine, what thread ID I am in many different, number of threads. So it could be 4, could be 8, could be 16, whatever I steer in the job script. And this is now, of course, sort of a problem when you have the shared address space and you would say, well, this is just the thread ID. So hence what you can do is you have this private statements here, private thread ID. This is a very, kind of so-called local variable for each thread, which we need because otherwise we would override again, right? Everybody would have a different thread ID, but if I just share it or basically store it in a shared address space, then we will override it and have not this information at hand. Hence this private variable is very important. It works totally independently on this. So that means we need to have this often when we have these different threads. And also good to know is now again, as I wrote and talked about, that you know that this pragma OMP is also considered to be the sentinel. So you see when we start with this and going into loops and other things, the sentinel will always be an important part because this tells the compiler, now there's something coming which I need to parallelize. The compiler will make sure that then this is prepared, right? That's why this sentinel directive is very good to understand and see it also as a very special string, so to speak. However, we don't have really the information yet how many threads we have. So this information was very crucial because it gives us the specific thread ID that I have in the overall number of threads. And this is important with the private variable, but what happens to the overall number of threads? So I want to know, like the ranks in MPI, how many are there in the communicator? Now here we don't have a communicator, we have an environment of OpenMP. Still, we should be knowing if we ask for 4 threads, 8 threads, 12 threads. And this will later be important to have because then we can also steer some program logic again with it. So you see the command here that is quite interesting. And here the number of threads is OMP get number of threads. So this, of course, gives you then the active threads that you just have in your current parallel region. And you see also, again, why is it so important to have a private, variable here? Because I can use it now also to steer the program logic, almost like I did with the rank, right? You remember we had many if statements with if rank equals 0, then do something. So here we are almost similar, but always think about that we are not in the area of processes, not in distributed memory. Here we are in shared memory and just talk about smaller thread IDs. Yet it is enabling us to really have application logic separated. In this particular example, we want to have a hello world from each thread that is in the parallel region, right? So the output should be something like every of these 4 or 8 or whatever threads we are asking for should give us this out, using also the private thread ID, but then only one thread should have then the overall number of threads in the parallel region given out. And this would be the so-called master thread here, the thread with the ID 0. So when you execute this and do this, there are similar elements that we have to talk about. Here's an example of our Utune cluster where you basically here have the instructions of the compiler with -f OpenMP, enabling now us with the GCC, with this compiler and the statement to look for this pragma OMP sentinel statements and then transform your code really into a parallel code that is then executing these parallel regions with the number of threads. The number of threads, again, you see that in the source code is not steered at that time, but we will get this information out of this. Here's a simplified source code with hello threads. You see that your main thread will just giving that out once, and then you have a parallel region. That means this one would be the output we assume should be coming a couple of times, because here this now depends on how much I put in the job scripts, 4 or 8, etc. And we would say always for each thread, I get some, kind of information, what thread I am in the overall number of threads. And then basically we will see also here, when we think about the outcome, that this is not a bracket or something like this. So it will be only this parallel region with one line of code, and the rest is serial again. So the main thread will come again just with one output. And this is something which is very simple. And the overall idea is, of course, to use, let's say, OpenMP much more wiser, much more in a bigger, let's say, working setting where you have work sharing constructs to use. And one of the very, let's say, not famous, but really often used one with OpenMP is then also the parallelization around loops, right? You see that here with a do or with a for loop. Again, it depends on which programming language you are. So this is one of the things which you can use with the work sharing constructs. And you can then look a little bit on the data parallelism sort of thing when you go in one example of this loop. There are also others. So one of it is this sections that you see in the middle. And it basically works then that you can break into separate discrete sections in your source code. Again, the overall concept remains the same. There's a master thread suddenly forking different helper threads. And then you have essentially assign these sections by different threads. And it could be that maybe the sections don't really match. So there's a thread that you have. You see that here, for example, that will not end up having a section. If you want, then of course this means we could, optimize the program, perhaps, if that is a kind of common thing, again and again. And another part that we want to also think about sometimes when we have a very, let's say, interesting aspect, we can come to a single element of it. So serializing a section of code within this particular part of the parallel program, right? Or in the parallel threads, really. So these are different work sharing constructs that you should use here and there. And top, of course, of the things we have just seen, the general OpenMP environment, as I would call it. So having a couple of examples here and there and why we would do this is maybe perhaps good now to understand. And the best with OpenMP is usually starting with loop parallelization. So that is something where we had this already in generally of thinking about domain decomposition. So these are interesting aspects when you think about the logic about this parallel activities that we have seen here and indicated. You can have a loop in pseudocode here that is going from 1 to 1,000. That's nice. Okay. And the other thing is quite interesting here. We see it's sort of independent from runs in the different loops. So what I mean by this, you think about that every iteration in the loop is just dependent on the E itself, not doing E plus 1, E minus 1, whatever. And this is a beautiful approach to really think about that this can be nicely parallelized, right? Because there are no dependencies and they can be completely independent from each other. A and B are different arrays. Maybe you want to, multiply this by a constant factor. And here that means we can do this in different parts and chunk it down. We even can say, maybe we don't want to have 500 and then from 500 to 1,000, chunked it up in, let's say, 2 parts. We could also say the first loop should run until E to 250, the one 251 to 500, etc., etc. So ending up essentially at 4 different threads that will execute this. And by this, no, I mean, if this is a very computation intensive activity and you would have much more of this inside this inside this loop, then you can come to a situation where, of course, then your time that you invest here in this T2, where the threads are working in parallel, could be, of course, leading you again to a sort of speed up. And this is, of course, also in a way very simple, because you think about now in the shared memory address space again, which is key again to this OpenMP. Here we have all as threads direct access to A and B, what I obviously need for reading, and also A for writing. Of course, the constant that is luckily also not changed. So it's a very simple and nicely parallelizable part, right? But this means also I can directly write in the allocation for this array at a certain index of the array into memory. And I don't need to send and receive that. I don't have to broadcast this. Every thread has directly access through the shared memory. And because I parallelize this with the different indices that you see here, there's also no direct race condition. So because I have the indices that are very different from each other, they will not overwrite each other. Here we have a sort of thread-safe computation of this very simple execution by loops. And this is one of the beautiful ideas how you can do this. I brought you a bit more, let's say, advanced loop example that you have here. Again, coming also back to our ideas in lecture 3 with the domain decomposition, and then also give you a little bit of color coding. Because here you see again, sometimes the beautiful elements in mathematics is that things are nicely parallelizable. But let's start at the beginning, right? So we have our header OMP that we always need to integrate, obviously. And then we define a couple of variables, E for our loop that we want to have. And then we get an input size that we want to maybe steer from the command line. That's why we have this interesting argument here, argv, that comes via the command line as a kind of parameter to this application, but it's not so important here. It just basically says the number of parts I have here in this particular array. But I will allocate these two. So hence, of course, I have to still allocate memory for this, right? In this particular part, we would have here the array X and the array Y, right? That I want to later on define as X equals X plus Y. And you have then, of course, the idea of going iteratively through these arrays and, just perform a multiplication. So, and when I do this with different threads, of course, here I'm relatively safe, again, in the sense that these X and Y are shared. So, because I will always be having different indices, entering in this. However, and that was left out in the last pseudocode. Think about that these indices now, this E is loaded. It needs to be very specific for your own loop you're working on. Because everybody has the same source code, it is now important that we have a private E for this loop, because here this will be executed now with the number of threads we are essentially looking in. So it could be 4, for instance, that you see here. And then we would overwrite the indices with a shared address space. That's why it's a private E. So this loop is a nice way of parallelizing the code without anything in the source code itself. You have, of course, the pragma OMP sentinel statement parallel, where you indicate these variable spaces, but you see that the mathematical element or the program logic stays the same. There's no parallel code in a sense, right? Which then end up, of course, making beautifully these color coding happening, that the results will be hopefully in memory then again, according to this. And then you have the vector elements or the array elements, how you define it, with X in the end in memory after this so-called parallel loop that we have created here with the OMP parallel statement. So in a way, again, think about these elements. I think this is sometimes very important to understand that you can have private data. In our idea, this would be the index of the loop where all the threads are working on. And then that should be not shared, because this should be very exclusive for you as a thread. And then, of course, we have the shared data space where X and Y are in, where I can now, of course, modify according to my private data index, so to speak, without any problems. So for a programmer, that means there's not much to do. I mean, there's, of course, something to think about these variables, as I just say, but there's a common sort of a modus operandi when you do these loops. And of course, it depends what application logic you have in the parallel region, right? You have to make sure that this is really sort of straightforward to do, because every thread needs to be working independently in a way to store this and doing this, and contribute to the bigger picture, which is then the overall vector that can be working on this. I think this is a so-called simplified demo code, which really is very easy to follow. And there are more advanced loop examples, what you can do just for the sake of completeness here, so that you can actually determine, and now that's exactly the point where I said OpenMP is very rich. So the overall specification is really more and more additions, more and more fine-tuning. We were alluding to the task-wise elements that we had also seen in coms and oms and PyComs in the end with Python. So in the last part. So here we think about tuning more and more what you want to do. Here in an example, you see essentially not only the private variable E again because of some loop that is coming, that is the OMP parallel. So we know this will be coming as a loop here and will be parallelized according to it. And in a way, what we now have different is that we have this dynamic schedule and no wait. So this is something which is alluding to how the threads will be worked on, how quickly they are finished, which could be here in the end according to the chunk sizes, where you then see with different threads executing this, let's assume 4 threads, there will be a static assignment of these parts, coming into the loop, where after this, the threads will start again according to a let's say a work sharing that is always equal or very static, so to speak, but you can also come to the idea to do it dynamically, so that basically the iterations of the loop will iteratively going, of course, through this, and then the chunks that you work on essentially inside this loop is something, the pieces would be dynamically assigned. So when one is finished, here thread 3, for instance, finishes already, then thread 2 and the other ones are directly scheduled, coming to a schedule which is not so, let's say, the same, because it could be that some thread ending up, for instance, in some activities which are much more faster to compute. Like for instance here, maybe thread 1, you see it comes earlier again in the schedule. There could be different reasons for it, but this enables you really to actually even fine tune here and there sometimes the schedule. Just as an example, and then we said, okay, when we have these loops, what about these sections? So you remember the overview, we had the 3 parts where the loop were the first, and the sections now are sort of the second element. Not everything needs a loop in this idea, although we connected here with a sort of small loop section, where you have now an idea to have 2 different sections defined, and you see the Sentinel is sort of getting in the idea of defining those sections, combined here with an OMP parallel loop again, and with a shared space of A, B, C, D, and then my own private index again for the loop, where I then have different OMP section inside these sections, right? So this is important distinction, where you see that we here do different things with the arrays. One is defining C new and also defining D new according to an addition and also multiplication. So, and each of these sections obviously now is executed with a thread and also with different threads. So it could be that that the thread is executed in more than one sections, is quick enough if it is possible. But essentially, you have the different blocks of work sections will be done by different threads. So that's usually the point. And it will come up to an idea that you see on the right-hand side, that these sections are then worked essentially again independent from another that should be really then introduced from the sections part in the Sentinel. So you can combine these elements, right, of the loop parallelization, which will be working then on your 4 loops that you see here. So making it parallel, but also parallelize again according to logic from the application, also the sections. So you see more and more we come to more complicated aspects of combining those. And if you have then large source codes, it could be actually quite sophisticated to read that, because it's not so easy always to follow like our playing examples here. There's another thing that we really need to talk about and we didn't catch before. This is, of course, now critical regions. They are very easy to understand. I think it's alluding to the race conditions around one variable, especially those that are shared, of course. With a private variable, there's nothing to worry about. But if you have a shared variable, the problem is that every thread can read and write at the same time. And when you now have a critical one, they see here in this tau example, you have a shared X variable in this parallel OMP part, then you suddenly have maybe a problem that, some others will execute this. You have maybe 4 or 8 threads, and all of those should define X new, but also read from X at the same time. And this is now something which really means at the same time there might be people reading and writing on one shared variable, which is a not good idea. Hence, you can mark this as a critical part. You see that here, which is now the important part, that this will be executed really by the different threads. But inside the critical region, the thread that comes first and want to execute it, they will block it. So the thread really, so to speak, is serialized, the thread approach here, in the attempt of executing this critical region, because we need it here, because we all want to have X read and we all want to have X, redefined. Hence, this is a very important part. And then you would have the singular aspects with single, we discussed also in the overview, which could be useful every now and then when you have some specific element to do. You see here again, maybe 4 threads working on their lifetime, including the master thread. And then when I specify this as a single, it could be that the second thread is now working on this input that you see here, while the others stay idle and then continue the work later. But there could be specific reasons for it, some sort of input preparation, for instance, which necessarily needs to be done just by one thread, not necessarily the master thread. So this is something to think about. Again, master worker paradigm, maybe that's needed to distribute again something across the different threads later, or write something in shared memory where we can all work on later. But this is something also which is not the same, but basically very important to protect and work with your variables. So there are more versions of fine-tuning your code. You see a thread private directive, and once again, in former times we have demonstrated this also with parallel lecture, or basically a practical lecture 5.1. But in the sake of accelerators and AI coming more and more into this course, we also have to think about dropping some lectures, but feel free to see this then also in the old examples of these lectures. But here you have an example where each of the different threads have then a thread private A and X variable, and you have this dynamic setup that is basically turned down with the dynamic threads. And you can see with this, it's a quite nice way of performing a sort of persistence when you go to different of these parallel regions, right? That you have normally you would lose everything if you just have defined your own, let's say, IDs, thread ID and private whatever B here, or the index of the loop we had before. Then you would lose that very quickly when the parallel region is over. The threads will be stopping, and you see that here nicely in the output a little bit, where essentially we have the A defined, we're working on it, and we keep it the same. But then when we come to the idea of the second parallel region, we can see that some of the values are actually protected, the A and X variable, because they essentially have a kind of replication stream, so that they have their own copy. And on top of it, the beautiful aspect is it will be also, you see here, the second parallel region, while the master thread is doing some zero work here. That is this part alluding to this. We have 2 parallel region, right? This is also obvious. We see that our A and X is actually surviving through all of this. So I don't need to redefine A here. I can continue with A later. And this is, of course, an important factor to think about, but you can use not to always, redefine variables, but have some persistency across this. And this is, of course, an important part. You also see this in the example that the B is essentially not protected like that. It is a private variable B, which is the difference. I define it, and we'll also see then later that essentially then B is, kind of 0 because it's not really defined. And this is something where you see the difference between thread private. Again, we have some interesting similarities, what you can do also with MPI, with the reduction operator here. You remember the reduce operation we had in MPI, or all reduce and so on. So here you can have something similar where you have a basically reduction clause inherently in the OMP parallel statement, where you want to have a reduction here on the result. And then you see essentially how that works is that we have a parallelization of a loop, of course, as we already understood. And then the final result will be something which will be added on over the whole parallelization scheme, right? You see that this, of course, is, every now and then new defined. And I want to do a reduction about all of them from all the parallel regions that I have, because I parallelize it here in order to make this happening. Hence, it's not a private variable. It's a sort of very specifically shared variable through this reduction statement. And then here again is the idea of the schedule, static and the amount of chunk sizes and so on. So also here, we don't need to go in the necessary details of this. This is a vector dot product example. But here the key is really to think about this reduction overall. Then another interesting application is this P, calculation. Some of you know to estimate P, you can actually compute this with lots of, random numbers approaches. It's alluding to something in early lectures we had as also Monte Carlo methods, so repeated random sample, and you can count those outside the ring and inside the ring, and make a sort of interesting, repetition of this. And if you repeat that, hence a number of times in your parallel way to estimate P, the more you come closer to it. And this is a, let's say, toy example. Again, it's not to show you how to solve that or do a software engineering exercise of this. It's rather to show you again that OpenMP can be useful for these elements. And the way how we do it, this here a little bit with the Pragma OMP parallel. Again, the statement that we have in our C program, we have a private E, which is then again our, of course, index that we have across the loop. And we have then the idea that now we want to have a random element in it to define this with X and Y. And then we want to have this statement here, which really defines that we have a hit. And when you have the hits and you count them, you would do this in the parallel area, right? So the question is, what is hit in terms of the address space? And you see, it's again our very specific reduction examples I would also showing you before. So this is a sort of very special shared variable because I will reduce on it with the addition. And by having this hits again and again added, you see a little bit of number of runs here, right? So where you have, of course, a random element in this area. So you don't know really, if it's inside or outside. So hence we have this statement to check about it. But if you continue with the number of runs, the number of hits also will be higher and higher. And with this, our estimate of P 3.14 gets higher and higher. So this is a technique really in, in computer science, or even if you want in scientific computing, alluding to something with random sampling methods. Repeated random sampling can help in many applications, in biology, for instance, computational biology, and so on, bioinformatics, things we had in previous lectures later, or this is something what we had to also sacrifice a little bit in this course this time, because we focus a bit on CFD, as you know. But of course, feel free to look in earlier lectures that we have also in the YouTube channel there. You will see some examples in the later lectures. So coming back to our idea then about this stencil methods. And when we had the heat dissipation, also this example we had already, I don't want to talk very long about it, but you think about, again, this time elements, then to compute, for instance, the heat in the room or as a specific part, we need the time step 0 data to compute the time step 1. So the next time step and the next and the next and the next. So you come to this sort of 2-layer way where we need, again, this information from the previous time step, right? And then you come to this overall idea of the stencil method, because every thread needs to do this, not only one thread. And then you come to this interesting idea of solving this heat in the loop, which is here now this 2D Jacobi iterative method. And this can be done also with OpenMP. Then maybe at the end of this lecture, a little bit about comparisons with MPI. So to conclude on this, we have MPI ranks for processes and we have OpenMP threads, right? And all of them have their unique IDs. That's possible from the OpenMP environment, like we had with the MPI environment. And this means we can really use it to steer application logic. So the similar things we did with MPI with rank equals 0, we can use our thread ID equals 0, for example. We have seen also as a kind of comparison that there are no really interprocess communication constructs. There's no send receive, there's no broadcast or something. Here we assume really the data is somewhere in memory and I can just access it, right? So there's no data exchanges that I did in the MPI space. However, you have the shared variables, right, which are very important. So in a sense, it is sharing, but you don't need an explicit data exchange. You just exchange the data, so to speak. We are introducing directly access to memory. We had the synchronization statements, MPI barrier, for instance, in one of the later MPI lectures, and also similar things we had also here in OpenMP. And hence you have also other automatisms that you have seen just before when I was, alluding to this OpenMP reduction clause with addition of the hits, for instance, in P, or let's say also the kind of overall maybe result of this vector examples we had before. So they are sort of similar, but think about always that MPI and OpenMP are different. And this is an important part to understand in this course. And when you have a real, let's say, hybrid application, something we know from the DBScan, for instance, it can become really complex. So of course you have lots of threads and you can use them with different commands with PS and top and then see what different threads are executing and so on. But the key message to take away is that there are also luckily performance analysis tools available that can understand your OpenMP program and can look into the different variables. And then you get a much better understanding for the private variables, but also the shared variables. Total View Debugger is one example here. In previous lectures, again, we had one lecture really, or in previous courses, we had always one lecture on parallel performance a bit more, but also this is what we left out a bit here to focus more on accelerators, AI, and CFD. So in practice, however, you will really need these debuggers. And finishing then, and basically make a nice connection to our next lecture 6, which will be then about accelerators. We will also come back to this example a little bit. You now can think about that we have different threads in the CPU, but what about also think about the tasks again that you can do with an accelerator. Hence, there's a standard that has been developed and is in development, I would say, the OpenEC, that is almost similar like OpenMP. So the idea is really thinking about, like we did here with the master thread, forking different threads, doing parallel regions and joining them. This is a little bit different with an accelerator because the master thread, so to speak, cannot be part of it because we're going into the device and into the many cores we have in the GPUs, while the thread was maybe forking it here somewhere on the main, on the CPU, going through main memory, delivering then the data. And you see here how these statements are looking in this OpenEC for GPU programming. You have an almost similar aspect. All you have to do now to think about a bit like data uploading and downloading, but you see also the parallel loop statement that is here nicely supported, then enabling your code automatically to use a device that you have and, basically bringing with the copy out then and the copy into the device memories here, a solution which is completely taken now essentially by the accelerator. And this is a standard part now, so it's integrated into the standard of OpenMP more and more, which is quite nice for us. And for the real application example, I remind you again to think about hybrid programming. We had this example of linear performance almost with having a hybrid implementation here with MPI and OpenMP for one data set, while MPI was, having a tail off. So you see some limits. Of course, this is not so easy. So you would have here local DB scans leveraging maybe firstly the shared memory. So which dots or which of the, let's say, cluster element of the data are within the address space I can access. After doing this locally, I have this overall grid, and then of course have to think about the splits and how to merge this. And then on a bigger scale, you want to even have merge halos. We have seen with MPI, of course, we are also limited in addressing this, space again. So I have to exchange some data nevertheless, because otherwise the HPDB scan would be very limited just using shared memory, right? Because there's just the number of memory we have, and maybe that's not enough to store all the data set. Hence, here is also more described in our paper. It's a really practical use of using MPI and also, of course, the OpenMP in parallel. A couple of other elements here from this clustering algorithm, but I think you see here not really the overall program logic. That's not what I would convene, but you see that within the source code of HPDB scan, my PhD student was really using the things he already learned: dynamic scheduling, private variables. You get the number of threads. Get the number of threads, and also the setting sometimes the number of threads, which is necessary for some specific elements. And of course, this is related to the job script we looked at earlier. So I set here the number of threads equals 4, and so on. Combined, of course, with the MPI information you already know here on the top. And in a way, that's really all I give you today in terms of OpenMP. I know it's not the whole covering standard or specification. So here I have to really refer to an OpenMP training. Here's a nice example when you add more and more threads, what it can help you when you think about parallelizing something. Here's a ray tracing application. And of course, the usual good, let's say, references that you particularly should look at. Perhaps if you find time, this paper here is very well written from Marcus. It's also one of my most read papers, and as I said, is also related, as I said earlier, to one of the implementations we maintain, which is one of the best scaling, I would say, DB scan algorithm that are outside. So challenge me on this. If you have also here in the YouTube community some source code which is better than HPDB scan, scaling better, more performance, let me know. Of course, it's 10 years old almost. So in this sense, there could be new ideas, new elements, but we still use it in practice today. And as such goes a challenge to think about if there's a better approach to DB scan. Acknowledgement for the team, and we see us next time with accelerators in lecture 6.